this thing. So just hold on. Yes. So here we are talking about 5, 6 different devices: cardiac pacemaker, glucose monitor, medical imaging sensors, neural implants, smart thermometer, and ultrasound transducers. So these we will try to figure out that how exactly this semiconductor technology is helping these devices to become smarter. So cardiac pacemakers are devices which are helpful for tracking bradycardia. It is a condition where heart is no longer able to generate electrical signals that are needed for the electromechanical activity that usually heart does for the body. So in that case, when we click on this cardiac pacemaker, then what we see is there is a complete simulation toolbox how it works. As you can see here, CMOS integrated circuits are inbuilt in the cardiac pacemakers. So there is an overview how it works. It uses semiconductor circuits to regulate heartbeat through electrical pulses. It generates electrical pulses and then it eventually helps the heart to become normalized. Now this particular device should be implanted inside the structure of the heart. Okay, so there is a small operation that should be done and the cardiac pacemaker will be inserted into the heart. Now then medical applications: bradycardia, heart block, and arterial fibrillation. Now these are conditions of heart problems. So bradycardia, as I have said, the heart is no longer working the way it should have. Heart block, where there is a complete blockage of the heart electrical signals and eventually there is a severe fatality. Then atrial fibrillation is something for a very brief period of time heart is not working. In that case, defibrillators are usually given. As you can see, these are electrical these things, electrical pulses which are given directly on the surface of the chest. So modern pacemakers contains about 1 lakh transistors in their ICs. Now when we start simulate, so it will start the simulation. Okay. Now you'll see the this is the simulation part. As you can see here, uh, the real-time simulation is like this. So it's a completely interactive educational simulator. Okay, so this is not connected to a real pacemaker, but it only to for demonstration purpose of our students. So how is the current? As you can see here, the current is this is the current window, then this is the average window, and this is the range. Okay, and this is the overview. Then these are the components. Let us see what are the components in this device. So there is a pulse generator IC which generates precise electrical pulses. Then there is sensing amplifier, okay, which is big MOS, which detects natural heart signals. So it will find out whether the electrical impulse is required or not. Then there is a memory chip, APROM, stores device settings and patient data, so which is inbuilt to the machine. Then there is a power management system. Now these are the all smart parts of this cardiac pacemaker. Now these are the specifications. Let us see what are the specifications. So these are the technical specification. Voltage is 2.8 to 3.2 volts. Frequency is 60 to 120 beats per minute. Pulse width is zero point 0.4 to 1 milliseconds, and battery life is 7 to 10 years. So usually this is a 7 to 10 years space. These pacemakers will be exactly okay. There is no this thing. Big companies which are making these cardiac pacemakers are Siemens in India. BPL is also there. So this is a simple simulator to give our students an idea that how these cardiac pacemakers work, okay, which are also based on these microprocessor technology. Then there is glucose monitor. Now why these glucose monitors are needed? So glucose monitors are needed because then there is a glucose monitor. Now glucose monitors will be tracking the real-time blood glucose continuously throughout the day, okay, in order to understand that whether the patient needs an insulin injection or not. Now what happens, these glucose monitors are inbuilt with insulin patches, and therefore what exactly happens is whenever there is a requirement, automatically insulin will be pumped to the patient's bloodstream, and therefore continuous intervention is not needed. The patient should not come at a particular time and take the injection continuously. Therefore, what happens? No, the regulation of blood glucose is also very very good, and there is no problem in this what you call is diabetic patient. Then medical image sensors. Just hold on. Just hold on. Yeah, madam, my screen is visible, madam.
Yeah,
Yes,
yeah,
sir.
yeah, yes, sir.
Okay. So this is the glucose monitor, as I have said. So when we click on glucose monitor, the same these things will come: the overview, the components, the specification, then simulation also can be done. So what is the medical application? Application is to identify diabetes type 1, which is also known as insulin dependent diabetes. Then diabetes type 2, and gestational diabetes is the diabetes in pregnant females. So here also the component, the specification, the simulation, everything is there. Eventually, if we go for the medical imaging sensors, there also you will see that all these components are there. As you can see here, overview, X-ray imaging, fluoroscopy, and dental radiography can also be analyzed. Now see the components. These are the components which is usually there in the semiconductor components. Pixel array, which is CMOS and CCD, captures incoming photons. Then scintillator layers, cesium sulfate crystals plus photodiodes convert X-rays to visible light, and then ADC array, column parallel ADC, high speed signal conversion, then image processor. ASIC codes, real-time image enhancement is taking place by this component. Then specifications, if we see, what are the specification of these semiconductors? These are the resolution, frame rate, dynamic range, and sensitivity as well. So these are the digital tools that are being, what is that? Okay. That can be used for this to have an idea that how these semiconductor systems are helpful for medical applications. So this is a teaching resource. One of our collaborator has given us an idea that what exactly he needs to teach these small students. That is, these are mainly first year students trying to build some projects, that what they can do. The neural implants. Neural implants are very interesting, as I see. These are mainly for brain related diseases. As you can see here, Parkinson's disease is a disease where brain cells are constantly dying. Then epilepsy is again a neurodegenerative disease, and brain computer interface, which is a very hot topic these days, and a lot of work is being done. So components, specification, simulation, all these things are there. For example, if we start to simulate, it will start simulation, that how exactly the analysis will go on. So this is an hypothetical simulation, but if we connect our program with a real device, it will generate this kind of a graph as a digital display. So this is how this particular device will be helpful for our students to understand that how semiconductor systems are integrated into digital healthcare devices, and they will try to design their new components and generating things of their own. Now coming back to our this thing presentation. Okay, so this was the how this semiconductor technology powers modern medical devices. Now, as I have already spoken to you, that these are the possibilities. Many a times, what would happen is uh, there are multiple different bottlenecks for which these devices may not be practical many times. So now, how the developer or a person who is interested in biomedical devices and making smart biomedical devices, how he will understand that what are the exact things that is going on right away. So in order to understand what exactly is going on in semiconductor technology in this particular biomedical domain, we should analyze the clinical trials. Now clinical trials are what? Clinical trials are experiments where the semiconductor based devices are really being used to a patient. Okay, so that is not hypothetical, that is a real time analysis, and it is been controlled and monitored by specific governing agencies, which will see the results and eventually decide that whether the clinical trial is going on in a particular direction or not. Okay. In clinical trial, there is a complete pipeline. So consider that you have done a biomedical innovation. Okay. So and then you do the collection of some data, then you do a relevance analysis, and then whether the system is ready or not, you do the evaluation, and you also cross check the limitations. Eventually, the future trajectory is predicted, and finally, a healthcare ecosystem is integrated. So, what it helps is what exactly is going on in the market, you can have an idea from clinical trial analysis. So, we'll one more time we'll demonstrate a tool which will help us to see what are the clinical trials on semiconductor based biomedical devices. Okay, so for a particular time period we have analyzed these clinical trials which are currently going on for semiconductor based devices, and we observed some features which are very alarming. So we'll come back to the second demonstration tool of ours. So we'll go to this, we'll close it, and uh, we'll go to our next simulator, which will help us to understand. Just hold on. Yes, clinical trial analytics of semiconductor based biomedical devices. Okay, now clinical trials, why these are important? Because they will give you the real information of the ground, that which devices is working, which device is not working. Okay. When you click on the view resource button, we will enter into a resource. As you can see here, our lab's branding is very prominent here. So if we build the tool for a third party or some collaborators, their brandings will be reflected here. Their name, their details, and their labs information, everything will be there on the top. So this is clinical trial of semiconductor based biomedical devices. Okay, so 170 clinical trials we have studied. Out of that, we saw that the trials which have given good results, success rate is 83.5%. So positive outcomes. Okay. Uh, just hold on. Yes. Then average sample size is approximately 63. So what does it mean? It means that 63 patients have enrolled in average in all the studies. Okay. So what happens in clinical trial is, why clinical trials are important. In clinical trial, real patients will enroll. For example, a patient with a dental problem will enroll into a clinical trial where semiconductor based dental implants are being tested whether it will work or not. Okay, so average sample size is very important. If it is very less, it means that it is working on a small group of cohort, which may not be very sensitive or which may not be very good enough. So if your sample size is good, it indicates that your experiments are doing well. So top applications, main application is dental and periodontal. This is very alarming thing, that it has been identified that uh, ability to integrate smarter smarter outcomes are more in this particular domain. Okay, so dental and periodontal applications are more. So 78 studies is focused on dental and periodontal applications of semiconductor devices. So the reason may be there is a huge market in cosmetic devices also. Okay, not for common person but for celebrities, and there is a huge market in for the affluent class where they take cosmetic things very seriously. So we'll see what are the this thing publication trends, the clinical trial publication trends. So in 2020 it was very less, and 2022 it has been increased to a significant extent. In 2025 a little bit decrease is there. So here it is just the post COVID scenario where there has been a rapid jump in clinical trials of semiconductor based devices. So these are the this thing distribution of sample size, which is very important. So 10 to 30 patients has been enrolled in 42 studies. So 31 to 60 patients has been enrolled in 68 studies, and so on and so forth. So more than 200 patients has been enrolled for 4 different studies or 4 different devices to be tested. So clinical trial outcome, positive outcome is 83%, then mixed results are there, and then no significant increase or no significant differences also has been reported. So efficacy metrics. So in efficacy metrics, what we try to figure out that whether these devices, these were designed for which kind of purpose. So pain reduction purpose, some devices were there. Then tissue regeneration, mainly dental. Tissue regeneration purpose also. Tissue regeneration means growth of the teeth or growth of the jawbone or something like that. These tests has also been done. Then bacterial reduction. So the dental infection is also a very major issue where semiconductor based devices has been regularly in use in recent times. Inflammation is nothing but pain. Pain, infection related physiology is known as inflammation. So inflammation control, there is also an issue. Then there is healing acceleration. Healing means recovery. That is something related to tissue regeneration. So these are the main domains where semiconductor-based devices has been applied. So high success rate, 83.5% trial shows positive clinical outcome demonstrating strong efficacy of semiconductor-based devices. So dominant application is dental periodontal application representing 45% of all trials, indicating strong evidence-based in this field. So, so there is a this is a basic understanding of how these semiconductor-based devices are being used. Now, what are the devices? This is also very important. What are the devices being used? So, mainly these many of the laser devices are being tested in recent times. Then photomodulation devices are also there. Mainly these are laser devices which has been included in this study. Then these are different wavelengths where these laser beams were being used for different reasons that we have already seen. Then there are some applications as well. So these are the applications, clinical application, dental and periodontal 45%, others oncology means for cancer purpose, ENT purposes, urology means urine related problems, ophthalmology, eye related problems, wound healing, that means infection related, dermatology, skin related, and pain management 14.4%. So these are the distribution of different domains where clinical trials, that is which is helping the patient. It is not a complete this thing just like that. If you wear it, it is okay. If you do not wear, nothing will harm you. So it is not like that. These are all clinical trials where dental and periodontal applications are high. Then the application details, dental, periodontal, pain management, dermatology, wound healing, ophthalmology, urology, ENT, oncology, and others. So these are the domains where semiconductor based devices are being used. It may be an IoT based device, it may be a device which can process a lot of data and eventually generate a electrical impulse for the heart, things like that is there. These are the distribution of these particular things, and then there is also the geography. So let us see in which area these studies has been there. In China, there has been many studies. Then USA, Iran also, Turkey, Brazil, and India also. So at least 10 studies on semiconductor-based biomedical devices has been reported as clinical trial, not theory-based research or research paper. These are clinical trials. So this is very interesting scenario here. So Asia, 68 trials, which is leading. Then Europe, then America, and so on. So this is the geographical distribution of these clinical trials and the outcomes. Let us see the outcomes. So 142 positive results, 22 no significant results, then 6 mixed results. So and what are the different use cases? These are there. So it will give you an idea if a person who's trained designing semiconductor devices and so on, he or she will figure out which are the different scenarios or which are the different uh, domains where he or she can put his energy in order to make an impact. Okay, so among multiple different biomedical devices, currently these clinical trials are going on with some good and average results. So this is very interesting for biomedical purposes. In my department, this is very important information. Coming back to our this thing presentation, that why these things were needed, as I have said, clinical trial analysis will let you know that at where you should focus your this thing energy in order to do further research in this particular this thing domain. Now, this edutech technology is also gaining a lot of what do you call acceleration. Why? Because it has been understood that by harnessing newer technologies, we can generate newer digital tools which will help our students to understand uh, where to focus more and where to develop their interest. So traditional tools are no longer been this thing, and these are very much evident in everyday this thing. Then therefore, an interactive digital tool for real-time monitoring of development of robotics and other biomedical applications will aid to development of resources and teaching learning processing, multiple different domains including robotics. Now here. There is a third-party research firm which is known as McKinsey. So they are also saying that this is the high time to develop new teaching solutions for our students in multiple different domains. For example, we are collaborating with recently we have collaborated with a college which is having a department where they are developing solutions for prosthesis. Prosthesis means patients with disability, hand is not there, paralysis is there, some kind of that. For them also we have developed a tool and we have deployed the tool to them. Then we have done work with a department who is interested in robotics. We have spoken to a department who is interested in 3D printing. They want us to develop a tool for teaching of their students. So likewise, we are collaborating with multiple different educational institutes as well as small scale industries to deliver our what they call solutions to them. Now, one more tool that we have developed is for a company who is looking for these semiconductor chips. So how he will find out that which chip is he should go and which company he should speak to. So for that also we have developed a digital tool. Consider that you are a small scale developer and you are trying to incorporate an IoT based biomedical device. Let it be a smart thermometer. So thermometers are being produced in India in a massive scale. So now what you want is you want to add a whole new vertical into it for patients who are suffering from uh, conditions like renal failure, kidney failure, lungs failure, or things like that. They should have. আমি একটু পরে কথা বলতেছি আমি একটা মিটিং এ আছি আমি একটু পরে কথা বলতেছি So what happens if there is a, sorry, if there is a company who's trying to build one smart this thing, what do you call is digital computer thermometer. The thermometers are very easy to build in India. It is being in a massive scale. it is being designed. But what happens? These patients who are suffering from renal failure and things like that, the body temperature or pyrexia or fever is a very important issue. So what happens? Just after the transplant, the doctor continuously monitors fever level. So if there is fever, it means that the body is rejecting the implant. Okay. So real-time tracking, what it, I do not know whether you have some experience or not with some of your friends, colleagues, or somebody. After transplant, a doctor will continuously sit with the patient only to monitor the this thing, body temperature. Why? Because if there is if the body is not responding to medicines, it means that body is continuously rejecting the implant. Implant is what? Implant is somebody else's organ which has been injected, which has been put into a patient. Now the body behaves like this, and that it is a foreign thing, and the foreign thing should immediately be rejected, isn't it? So for that, what happens? The doctor gives immunomodulators. So these are drugs which will fool the immune system of the body, so that this adjustment is done. So once the adjustment is done, then what happens is it will accept the foreign this thing, graft or the foreign tissue in the body. But in this 24 to 48 hours is very critical. So one of our this thing is trying to figure out a monitor which will send the alarms directly to the doctor who may be at a remote place, and eventually it will help him to monitor the patient in a real time basis. So what is trying to do is it trying to build a thermometer which is connected to a this thing network. So in that company, they should know that from which company they should procure the devices or the microchips, isn't it? So for them, we have demonstrated a digital learning resource and mainly a real-time monitoring tool. What exactly happening on this particular domain? So we'll go and see this manufacturing dynamics right away. So we'll again go to our just hold on, to show you how this particular tool will be working. For example, as I have given you the scenario that recently I wanted to install some kind of hardware in my college computer, but the prices has been increased several folds, mainly due to this rare earth mineral issue and also the supply chain issue of China, US, those kind of things. So in that case, it may not be directly impactful for us, but for industry who is looking for this chip at a large scale will be a very important issue. For them, we have developed a real-time analytical tool. Just hold on. Yes. So this is tracking the heart of the tech, that is global semiconductor development trend. We will try to figure out. So monitoring the global trend. It's a bit old tool, not updated recently, but still it will give us you an idea to our students that how this thing will happen. See, our branding is very prominent. SDN Analytics Lab. We like to call our lab like this, and this is our college name, etc. So global semiconductor industry monitor it is. Okay. I hope I am audible enough. Just hold on. Okay. So what happens? Real-time tracking of chip development, manufacturing and supply chain dynamics. So everything can be monitored from here. So industry advancing, monitor geopolitical risk is there or not. So these are very critical issues. So leading indicators. So these are the leading indicators of this particular industry, chip development industry. TSMC refer is production is increasing or decreasing. China SMIC node progress, and then ASML European Union's shipment. How many shipments are going? Then global chip shortage index. Now there is an index that has been identified. It is like Sensex and Nifty only. So how the global chip shortage is there or not, they will usually track it. So in this data set or in this toolbox, this is also been incorporated. So key players and technology status. TSMC, this is the foundry leader. It is placed in Taiwan. Node size is 2 nm. So if we click on it, so we'll figure out the technology focus, advanced node development and manufacturing capabilities, market position, foundry leader with a strong presence in Taiwan. So from Taiwan, the South China Sea route, it will be distributing throughout the US, Europe, including other parts of Asia. And therefore, this China-Japan conflict is there to control this South China Sea corridor. So key matrices are leading edge 2 nanometer technology deployment. So as far as we understand, the thickness of the wafer is very important here. Then Samsung, the foundry number 2, that is the second one after TSMC. Samsung is also a big player in this particular this thing. Node size is 3 nm. Region is Korea. So technology focus, advanced node development and manufacturing capabilities are there. Foundry number 2 and strong presence in Korea. Not only Korea, throughout the world only. Today Samsung phones are much more. I am using the Samsung phone right now. And key matrices are leading edge 3 nanometer GAA technology deployment. Then there is the US giant Intel. So let us see what is the capabilities of Intel. IDM revival take place. Node size is 18 Armstrong. Technology focus, advanced node development and manufacturing capabilities. Market position, IDM revival with strong presence in US. Key matrices, leading edge 18 Armstrong technology deployment is there. Then SMIC, again China. So see here that the Asian companies are doing very big in this particular domain, and it is being this thing also. Recently, I have tried this thing also. What is called as DeepSeek. Now, if you ask some critical question about China, it refuses to answer. You can try it yourself. So, very strong foundations. SMIC, technology focus, advanced node development and manufacturing capabilities. Node size is 7 nanometer. Market position, China foundry is strong presence in China. Uh, Key matrices, leading edge 7 nanometer technology deployment. So we'll add something more here. Then ASML. Now ASML is a different ball game altogether. They are having the hardware to develop these chips. Uh, Not only fabrication, the machine that is needed for making these molds and everything, these are procured by ASML. So these are called litho equipments. So node is EUV high NA, region is Europe. Technology focus, advanced node development and manufacturing capabilities. Market position is litho equipment with strong presence in Europe, throughout the world only. A key matrix is leading edge EUV high NA technology deployment. So event timeline. So what happens here, if we take these regions, US, Taiwan, like this, we can change these categories as well. Node advance, fabrication capacity, policy, equipment, supply chain, so on and so forth. So we'll quickly see. Let us see what is happening in USA. So US, then category is let's say supply chain. So we'll see what exactly is the scenario now. So there is a recommended data source. Okay, so from this data source, we can have an idea that what exactly is going on in US for supply chain issue. Okay, so recommended data source are these. You can click on these and you can see the this thing what exactly is going on. Okay, so foundry data, TSMC monthly revenue report, Samsung foundry announcement. So it gives you a wholesome thing for the people who are industry. So it is basically a business to business solution, not business to consumer solution like the previous one. So the other one, which we have already described, were some consumer related resources, isn't it? For example, just hold on, I'll give you a small demonstration of one more research of ours. Uh, there is a robotic simulator, yeah. So there is a robotic simulator which a small student can also deploy. Just see here. So this is a robotic arm, and we will try to show our students how this robotic arm will helpful. Okay, so for that, when you start it, and what we can do is, as you can see here, consider that it's a robotic surgery maker. So if we change it, it will also get changed. Consider that this is a artifact. I have to remove it. So for that, what we'll do, then grip opening. So if we close it, the grip will be closed, and then elbow joint. If we remove it, and then again gripper is opened, the tissue will be going. So like this, what we can do is we can show to a student that how these robotic arms will be helpful, and how you can monitor and you can even control these robotic arms from a remote place, from this toolbox only. Consider that the robotic surgery is going on somewhere, and the doctor is operating this whole part, this part, from a some other remote place. Okay, for example, I belong to the eastern part of India, where big hospitals are not there, or there are some this thing bottlenecks. So in southern part of the India, there are very big hospitals, even in northern India also. So doctor will be sitting there, I will be deploying my Da Vinci tool, that is that can perform a robotic surgery. The doctor sitting there, they can perform this surgery. So in order to demonstrate this, we have developed this particular tool, which is called a medical robotic surgical simulator. So like this, what we can do is, this is a deployment for the consumer itself. The consumer means the college itself. But this particular tool is only for this industry person only. So it's a business to business relationship. So what happens? Every time we can click on here, we can change this thing also, and eventually we can have an automated digital resource center, which will help our for example, if we go to the, let's say, Europe, and we will try to figure out node advancement. So these are the this thing recommended data source, and eventually you can everything in a single place. You need not to go to Google every time and search for things, and it will give you a clear cut idea that what exactly is going on. And these are the indicators also. These are indicators. For example, it will change continuously. Okay, although it's not working right away, but once we integrate one more API, so what will happen? Continuously change this data. Okay, TSMC refer starts 12%, then it will increase the production, and then what will happen? Once this TSMC refer start increasing in production, eventually the supply chain will also act, and then eventually global chip shortage index will also be changing. So eventually it will help us to monitor the chip development industry for our global semiconductor industry monitoring purpose. So this is how we are developing our tools, and trying to help our collaborators. So these are some of our old collaborations that we had. Uh, the new collaborations we have not demonstrated here. By saying so, I would like to conclude, and if there is any question regarding this, we are happy to answer these questions. So our main focus is on developing teaching research tools, teaching learning tools for small institutes, or we have collaborated with colleges also. Recently, I think the name of the college is, just hold on. We have collaborated with I think it is Kerala College of Engineering, where we have demonstrated a tool which is helpful for manufacturing of prosthesis. That means artificial limb for the patients, and how to deploy which kind of limb for which kind of patient. For that tool we have deployed, and other than that we have collaborated with multiple different organizations to develop these teaching research tools. We are happy to collaborate with any of you present here over here for developing newer tools for your research purpose, for your teaching purpose as well, by using this advancement in artificial intelligence and machine learning.
Thank you, Sir. Thank you. That was very informative. Thank you. 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 So it's time to ask questions. Anyone have any doubts or queries, please feel free to ask.
Yes, yes. Uh, since it is working fine, we'll demonstrate one more tool. For example, mm, okay, just hold on. We have one more tool which is mm, this is very interesting one. The tool is called Saraswat, Secure Analytics for Risk Assessment and Surveillance of Wearable and Ambient Therapeutics. So we have developed it for one teaching resource. So here what happens, we can identify the threats, cyber attack threats on different biomedical devices. Okay, for example, these are five devices, biomedical devices, which are very much prone to cyber attacks: insulin pumps, pacemakers, MRI machines, patient monitors, and ventilators. Now, these are we are talking about smart things. Smart means they are being connected to a this thing cloud. So if these are connected to a cloud, there is a very possible chance that the security issues will be compromised. In India, the regulations are not very great, but in other countries, there is very stringent regulation on medical device security. Because what happens now, as I have already said, that the third party that is considered a healthcare provider or a health insurance provider can use this data in order to manipulate the market or do something. So in that case, this particular tool will help you to understand what are the different types of threats are there. Okay, for example, this remote code execution vulnerability. So in insulin pumps, what it can do is
And is it
it can identify if some remote codes are or some malware are being
as the fan?
deployed through
So we
Bluetooth or something,
message it in Bluetooth
which will mainly
and
from
phone.
Bluetooth. So which will lead to some
And it
malfunctioning
gonna
of the
feedback in there and
insulin
as the
pump.
fan
Now
feedback to
insulin
the
pump
fan.
will monitor
So
the
it will
glucose level
integrate with the
continuously, and
Bluetooth.
whenever needed, it will inject insulin in an automated basis. Then there is authentication bypass in telemetry systems. Telemetry systems, as I have said,
And the
the
feedback it
this
is
thing will
the
be
government
monitored from a
include the name of the government even on this
from a
India
far
India
area,
and
and the
China
doctor
government.
will treat the patient from a remote site. It is not telemedicine.
Eh?
Telemedicine means it is not
Yeah.
giving and prescribing medication. Then there is data interpretation or interception via network sniffing. So this is also been reported in patient monitor. Patient monitor means in ICU the patient will be admitted, and the monitor is continuously getting all the vital signs and signals. So those data are being fed to the cloud, and from the cloud the doctor there is a automated what do you call analytical system which will figure out which kind of medicine should be provided, whether the patient should be taken to a ventilator or not. This kind of critical issues are there. So unencrypted patient data transmission may lead to some cyber attack to the hospital networks, and eventually the patient security may be compromised. So this is again the digital tool which will help us to identify the risks of connected biomedical devices. So this is how we are trying to generate these tools to help or to streamline teaching learning processes for our students. So we are also this thing open for collaboration. Any of you can contact us for any kind of requirement of yours to build a this thing digital tool for your teaching and research purpose.
So, participants, if anyone have any questions, please unmute your mic and go ahead with your questions. Sir, I think no more questions.
Okay.
Okay, sir. Thank you so much, sir, for today's detailed and engaging session. The way you explained the concept was very clear and easy to follow. The session was very informative. It was genuinely refreshing to listen to your talk. We also appreciate the time, effort, and patience you put into addressing the contents. Once again, thank you, sir. Thank you so much for your valuable contribution to this program.
No, no, no. There is a question. Lokesh Lodha, sir, can you please provide the web link? Okay. Professor Lokesh, but there is some limitation. As I have said, no, I am also not expert in that particular thing. The whatever feedback and whatever information has been provided by this particular institute to us, then we have designed this thing. Okay, so our branding is showing here because we are using it for this particular purpose, but it has been delivered to that particular college and they are using it for the way they want it. So right now we are very sorry, we cannot share the link so that you can use it. But what we can do, Professor Lokesh, is yes, yes, definitely we can feed the data manually also. I give you an example. I give you an example. Consider that we have designed a simulation tool to identify a very basic thing. How BP is changing over a period of time for a patient, and what should be the lifestyle changes the patient should do. Okay. So for that, what we can do, we can have a small 1000 rupees BP machine, digital BP machine in our lab. Then we can continuously monitor this, and very simply we can generate a tool which will monitor you can feed that data to this tool, and the tool will predict that what are the healthcare intervention the patient should have, whether the patient is having normal blood pressure, more, or you can also incorporate other things as well as body mass index, whether the patient is overweight, uh, then what is his heart rate. So multiple things we can incorporate, and eventually we can generate a overall health report for the patient also. So it is very much possible. Let's say that you do not have a smart device, you do not have a desired device which is connected to a network or a cloud. So what you can do, you can manually record this and then make a Excel sheet, and you can send the Excel sheet to us, and eventually we can do an overall analysis of the patient's body. What is the patient's usual BP, which has been monitored for 7-day period, what is his food habit. So incorporating multiple things, we can generate a custom report for the patient, and what are the possible intervention he or she should do in order to reach a normal what do you call parameter. For example, the patient is having high BP. The patient may not be a patient himself. The person may not be a patient himself who is already admitted to ICU. That capability we do not have right now. But what we can have is, consider a student who is coming who can have a heart issue or a diabetes later on time. So we can predict that well, very well. We can predict it, and we can use this thing. Uh, mm, mm,
Thank you, sir. Thank you for the kind reply.
for our work purpose. Definitely, Dr. Lukesh, we can do this.
Thank you, sir.
No, these tools are not accessible, dear Dr. Sangeeta Mangesh, because as I have said, we have developed it for some other person. If we develop something for you, definitely we will share and we will talk about it more. Yeah.
So thank you, sir, for taking the time to answer to our questions. Thank you for addressing our questions. Thank you so
Thank you.
much once
Thank you.
again.
Thank you, one and all.
So, without any delay, let's start our next session. So, next session is handling by our respected resource person, Dr. Arun Avi. Arun sir, can you hear me? Arun
Yes,
sir?
yes, yes. I can.
Okay, sir. It's my pleasure to welcome Arun sir, Assistant Professor in the Department of Electronics and Communication Engineering at TKM College of Engineering, one of the premier government-aided and autonomous engineering institution. Dr. Arun Avi holds a PhD in his field and has been serving with dedication in academia, contributing to both teaching and research in core areas related to microelectronics and VLSI design. His commitment to academic excellence and student development is further reflected through professional achievements, including being selected for the IEEE Outstanding Branch Counselor and Branch Chapter Advisor Award, a recognition of his leadership and continuous supporting, nurturing a strong and active IEEE student committee at TKM College of Engineering. We are honored to have Arun sir with us today to lead the session. With this, we warmly welcome you, sir, and we invite you to kindly take over the session.
Yeah. So just give me just a second.
Okay, sir.
Yeah. So you can hear me, right?
Yes, sir.
And you can see my screen, right?
Yes, sir. The screen is visible.
Okay. So thank you. Thank you. Thank you, Janshamis. Thank you, King Sir, for again inviting me to this FTP. Uh, so, my topic will be around building a hardware accelerators using sync systems, and so I'm planning to do a hands-on session today. Uh, so that so I will go through the process of building a hardware accelerator through HLS systems. Yeah. So if you have Vivado tool with you, you can do it with me, or otherwise you can take note of it, and I will share my slides also. But rather than slides, it will be more of a demo session, and you can do it afterwards also. Okay. And since the theme of the FDP is around AI and how AI and chip design goes hand in hand, this will be a good starting for you to have for building hardware accelerators for AI and ML systems. Okay. This in this talk, the accelerator building will be based on sync processing systems, and for this particular demo, I will be using a Pink FPGA. Okay. So these are the contents of the talk. First thing, what is the motivation for going for sync and HLS based hardware accelerator building? Then I will give a overview of the sync processing system in which we are building the accelerator today. And finally, I will go through the demo session. So the basic motivation. So nowadays you can see that so the regular ASICs are being displaced by programmable platforms. So this is mainly because in the fabrication of the fabrication and the post fabrication process of ASICs, the packaging and verification costs dominate. So whereas FPGA has a clear-cut advantage over this the whole ASIC process, so we can reduce the cost. And also the design, in a design point of view, the full custom or semi-custom design versus the FPGA flow, which one is easier? So obviously, the point is that FPGA process flow is easier, and there are to our advantage there are many programmable platforms. So nowadays FPGAs are no longer FPGA itself. So it has a CPU, it has a DSP, and some of the latest FPGA has hardware accelerators inbuilt into this. And so these are the clear-cut advantages. And so now we are moving from FPGA to all programmable devices. So the thing is, at the same time, it is a small device and as well as it is a big device. So small device means the size, the integration area is very smaller, but we can do big things using the FPGA.
Response.
Okay. So am I audible now?
Yeah, yeah, yes, sir.
Yeah, okay. Since I'm using the network through my phone and a call comes, so it may so please, if there are any network issues, please indicate me.
Fine,
Okay.
sir.
So yeah, thank you. So the Xilinx technology evaluation. So the FPGA, as I told earlier, the FPGAs are no longer FPGAs. So FPGAs are now it is mainly collection of processor and an FPGA. So it is basically a SOX. It is basically a system on chip. Right. So the demo board which I am using today is also a combination of a sync processing system and an ARM processor. Okay. So the technology has evolved through being a simple FPGA from a SOC from 3D ICs. So all the things are in our hand, and the only thing is that we should now design the optimized hardware accelerators for AI and ML. So coming on to sync board. So for the demo, I am using a Sync 7000 family, and as I told earlier, Sync 7000 family has an inbuilt ARM processor. So basically, processor is ARM Cortex A9, and it has all the memory controllers and the peripherals. And the basic thing is that it is fully autonomous to programmable logic. And uh, and the interfaces are also there. So in the today's demo also we will be using AICTE interface to interface our IP and the processor. And also it has a wide range of external multi-standard input-output systems and high-performance serial transceivers, and it has built-in ADCs also. Okay, so this is the architecture of a sync processing system. It is a dual-core processor with ARM Cortex A9, and it has floating point support. The speed is 1 GHz operation, and it has L2 cache. it has integrated memory controllers. And the programmable logic has around 200K LED cells, and it is supported with the high bandwidth AMBA interconnect. So mainly I will be using AICTE interface. So now we can view the FPGA as three independent pieces. So the first piece is interfaceable IP blocks. So we have the memory controllers, we have the HDIs, or we can do a custom IP. So today I will be building a custom IP, and I will be interfacing with the processor. And the second piece is the core IP. So the core IP, which is Sync 7000 processing systems. So we can interface the custom IP and the core IP. And application specific IP can be also built. So for the today's session, I will be building a multiplier and an adder. So what is high level synthesis? So it is a application specific IP, and it is built around a high level language. So mainly it revolves around C and Python. And uh, uh, the main advantage is that it addresses a lot of problems, like uh, we can do parallelism. So we have the pragma loops and other things. So we can explore more on parallelism, and we can build the memory onto BRAM, and we have good timing models for the FPGA synthesis also. If we go for HLS. So the main difference between the traditional SOC flow and the sync-based processing flow, HLS-based processing flow, is that so in the traditional way, we have the specifications, and with the specifications, we will uh, build RTL code, and RTL code will be given to the FPGA, and the FPGA processing takes place. So whereas in high level synthesis, so we will be using an HLS tool. Today we will be using Vivado HLS, and using the Vivado HLS, the software specifications can be directly connected to the RTL code. So there is no need of separately writing the RTL code. You can, with your high level code, you can define the accelerator, and it will be directly converted to the customized IP or the RTL code, and it can be run on FPGAs. So this is the complete architecture of ARM-based processing systems. So with this, I will go to the demo session. And for the demo session, I will be using HLS. So it will take a couple of minutes to load the tool. Yeah. Okay, so this is the HLS. So it is from Vivado only. So I will create a project. Say the project is FDP demo, something like that. Location. And so the name of the main function will be, say, so I am basically doing an adder and a multiplier. So I will keep the function as add mul. Okay, so I will create a new file. Uh, so the name will be atmul.cpp. So today I will not be going on to the simulation thing. So I am not adding any test bench files. So I will skip this. Yeah. So finally, so I have to select the FPGA board. So the board, since I am using a pink board today, so the part name will be XC7 is at 020 CLG 400 minus 1. So this is the part name for the particular board I am using now. It is a pink board. Okay. Yeah. So yeah. Okay. So okay. Yeah. So this is basically my code. I hope you can see this. Is there any comment? Voice quality. So is it fine now? The voice.
Yes, sir. Voice is audible.
Yeah. Okay. Okay. Yeah. So this is the basic code I'm using today. So first thing is that I'm defining a function. Maybe I can zoom in. Okay. So I'm using a function add mul. Okay, so this was the top function name which I gave, and I'm taking two inputs A and B and two outputs C and M. Okay, and so I am basically initializing all the inputs and the outputs as a AXI. I'm interfacing it through AXI. So I am making all the input ports and output ports as AXI compliant. Okay. So these slaves, these ports will be basically act as a slave, AXI slave devices, and the master will be the processor. Okay, so I'm defining port A, port B, port C, and port M as slave AXI light, and so I am also defining a pragma loop. So pragma loop is basically for doing parallel operation. Okay, and the function which I'm going to do is C gives the addition of two numbers A and B, and multiplication is in M. So I have basically two outputs. Okay, so I think it is clear with that. So what I now do is I will run the C synthesis. So I don't have a test bench, so I will not go for simulation. So I will directly run the C synthesis. Yeah, okay. So C synthesis is done. So I will look for if there are any errors. No, there are no errors. Okay. Yeah. So my this basic C code is synthesized, and if I have to look at the utilization, this since this is a very small design, no block RAMs are utilized, and I have used 479 flip flops and 410 lux. Okay, so this is fine. So now the thing is that so I have written a function to do addition and multiplication, and this thing is done in HLS, and it is accelerated using parallel processing. We have given pragma loops also. Okay, so now the thing is that this particular function that we have written in HLS should be converted to an IP. Okay, and with this IP, I should do a block design with the sync processing system which I have in my FPG. Okay. So to do that, what I will do is I will go for export RT. Okay, so I need this function which I have written to be made as an IP. Okay, so I will configure the IP first. So library name, so let it be HLS, and since in my HLS version, I have to give the version number as 1.0.0, otherwise there will be some warnings or errors. And that's an description of the IP, addition, multiplication. Okay, rest all things are okay. So I'll click OK. And I have to give the output location. So what was the name? FDP. Okay, so I will select that location. Yeah, and okay. So we'll take a couple of minutes to create the IP. So are there any errors? No. Okay, this is fine. Okay, so the IP is created. So IP is created, well and good. So now I will open the Vivado platform, and I will basically do the block design. Okay, so we will wait to load the Vivado tool. Yeah, so this is the Vivado project. So I will create the project first. Yeah, so The location is DHLS is okay. Project 7. Project 7 of DPD. So RTL project. Again, we have to select our part. So XC7 Z020 CLG 400 minus. Okay. Yeah. So the summary. So it is basically a Sing 7000 family. Okay. Yeah. So this is my project manager. So I had created already an IP. So no RTL coding will be done here. So you will go for the block design. So I will create a block design. So design one. Okay. Okay. So here we have to do the block design. So before doing the block design, so I have to load the already created IP to my IP report. So for that, settings, and IP repository. So I will add the IP repository here. So where was the? Yes, I think it was in the demo folder. FDP demo. Yeah. Okay. So we'll select. I will check if the So there is an IP. Yeah. The name of the IP is ATAL. Okay. So I will select the IP and okay. Yeah. So now I have to add the particular IP here. And for doing it, is the name of the IP is ATAL, and we have ATAL IP here. Yeah. So this is our IP. So that we have created using HLS. So here we have the symbol of which is HLS, and it is AICTE compliant. All the input and output ports which we have used there is AICTE compliant. Okay, so this is fine. So now we can add the sync system. Again, if I search for sync 7 processing system, yeah, okay. So we have our processing system. So this will basically act as the master, and our IP is the slave. Okay. So we don't need to give the interconnections manually. So we have the automations in Vivado. So first I will run the block automation. Okay. Yeah. So connection to the external DDR is done. And again, if I run the connection automation, so using a AICTE crossbar, so it has done all the interconnections. Okay, so it is fine now. So now what I have to do is, so first thing is I have to validate the design. Yeah, so validation is successful. There are no errors or critical warnings. So if it is validated, then I have to create an HDL wrapper for this particular block diagram. So here we have the option of creating the HDL wrapper. Okay. Yeah. Yeah, so the HDL wrapper is here. So we have design one dot v. Okay, so that is fine. Now I will try to synthesis the design. Okay, since I am not using any input or output ports, the pins, I'm not using any pins, so I will not give the constraint files here. So we will directly run the synthesis. So it's, the synthesis is running on the background. So we will wait for that. Yeah, so it will take some time. That is why I have purposefully selected a very small design. Uh, if it is a big design, it will take more time. Yeah, okay. Yeah, synthesis is successfully created. No errors are reported. Yeah, so this is okay. Uh, yeah, so next step is to uh, uh, create a bitstream file. So we all have to run the implementation also, but I will directly go for generating the bitstream. Uh, yeah, so it will say that there is no implementation. So I will so let the tool do that also. So it will start from the synthesis. Okay, so it will also take 2 or 3 minutes. Yeah, so bitstream is successfully completed. Okay, so yeah, so if I go and take the particular folder, pbd dpa runs implementation. Yeah, so we have the .bit file here. Okay, uh, yeah, so the bit file is created. So now what I should do is that I should now load this bit file into the FPGA. So I have my FPGA, so I will switch on the video. Yeah. So I have my FPGA with me now. Okay, so my FPGA is with me. So I have used the LAN port of the FPGA port to connect to my system as a local host, and through the Ethernet thing, I will. So I have a memory card also. I have a memory card in this FPGA also. So I will load the bit file directly to the flash memory of this FPGA. Okay, I think my connection is reset. Yeah, so this ping comes from ping has a Python productivity. Uh, yeah, so I have already so this ping board has a Python productivity and it has an inbuilt Jupyter notebook in it. So this particular thing is in the flash memory of the board, and so here I have created a folder pre-admin particular folder is here, and in this folder, yeah, so in this folder, so what I have done is so I have imported the .bit file. So I have the .bit file here, uh, and the next thing is I have a hardware handoff file also, so it can also be accessed from the runs folder in the implementation folder of this particular project. And also I have the block design file. So block design can also be exported from Vivado. So we have the export option here, and we can export the block design, and we can name so now the name is design underscore one dot tcl. So we can export the hardware design also. So so in this particular folder, I have the bitstream file and the hardware handoff file and the block design file. So with all these things, I will create a new notebook here, and this is my notebook. Okay, so what I am doing is, so I am importing API overlay, and I am overlaying my .bit file, the .bit file, the bitstream file, which I have created which I have created from the block design. Okay, so I will overlay the uh, this particular thing. So I'm having a network issue, so it may be sometimes slow. Yeah, okay. So to know the details of the overlay, since the network which I have connected is going slow, so it is taking a time. Yeah, so what I will do is I have the slides here. Yeah, so this is what it was later executed. Yeah, so I have added the IP, and from the hardware file, I know that in address location 10, the number 4 is loaded, which was basically A, and in the address location 18, I have 5, which is basically B. And if I read the address 20, so in the address 20, I have the output C, which is basically addition. So 4 plus 5, 9 will be generated. And if I read the 28th address location, which has the output M, multiplication will be done. Okay. So the result is 20. Yeah, so it is taking some time. Okay, so this is basically how from an we can load the particular thing into a hardware. And similar to similar to this IP, yeah, we can do say a convolution network, or a transformer network or something like that, and we can very well bring it into the hardware. Okay, so if there are any queries, I can answer those.
Anyone have any doubts, please ask.
Yeah, okay, so I think that's it. Thank you. So if you have any queries also, so I will just uh, write my mail ID. So in our lab, we basically build these types of accelerators. So accelerators with the FPGA support as well as the standalone SOCs, which is basically RISC-V based. So if you have anything to any queries or if any collaborations or anything, you can write this to my mail.
Kiran sir, thank you so much for
Thank you.
taking the time to guide us today. Your hands-on session made everything so easier to understand, and it was really helpful to see the concept in action rather than just hearing about them. So thank you so much for your patience and making the session so engaging. Thank you so much. So everyone, please fill out the feedback forms